This 3D topographical plot of a Dirac cone represents the energy contours of an electron. By calculating its slope and cross-sections, we supposedly map all conductive properties. But notice what happens when the topography flattens completely into a zero-slope plateau, a flat band. According to the traditional scalar map, an electron sitting on a perfectly flat energy plane has zero gradient. If an electric field is applied, the expected velocity and superfluid stiffness are zero. The electron should be physically immobilized. Yet, experiments show otherwise. In these flat regions, robust response vectors break right through the predicted boundaries of the zero-slope model. Two different energy bands can possess identical flat contours, yet exhibit radically different dynamical properties when tested in the laboratory. If robust material responses occur exactly where the energy gradients vanish, the energy band alone cannot be the whole territory. The standard topographical map is incomplete, missing an entire geometric layer. To find that missing layer, we must abandon a persistent conceptual error, the idea that an electron is a tiny charged bead with a hidden physical surface, or a literal material shape waiting to be photographed. Under the TCGS-SEQUENTION framework, our three-dimensional observable world is a shadow realization, a projection, of a complete four-dimensional counterspace. The properties we measure are simply pull-back observables from that higher dimensional source. Under this framework, the electron is not a self-contained object. It is a stable, shadow-readable carrier of a deeper, source-level mathematical relation. When we detect particle-like strikes, or wave-like interference patterns, or distinct spin textures, we are not looking at separate physical pieces. We are charting different expressions of that exact same source relation, squeezed through different measurement constraints. To understand why electrons move in a flat band, we need to map the projection grammar itself, the specific geometric rules dictating how that source relation pulls back into a readable state across momentum space. This is the quantum geometric tensor, or QGT. It provides the gauge-invariant local differential geometry of the block state manifold. As the equation expands, it splits into two distinct structural components: the real symmetric part, G, and the imaginary antisymmetric part, omega. Isolating the imaginary antisymmetric component gives us the formal mathematical representation of Berry curvature. In semi-classical electron dynamics, Berry curvature is what drives anomalous transverse velocity and generates quantum Hall responses, occurring independently of the band's standard energy slope. Translated into the projection framework, Berry curvature is shadow holonomy. Watch what happens when a projected electron relation is parallel transported around a closed loop in this parameter space. It does not return to its original orientation. It acquires a measurable phase twist. This phase memory proves that the underlying state space has a structured, non-trivial internal geometry, even if the surrounding energy topography is perfectly flat. This curvature tends to concentrate near band degeneracies and avoided crossings. These act as projection stress points, where the mapping of the source relation is forced through a tight constraint. An electron responds to the curvature of its parameter space just as much as it responds to the slope of its energy. Holonomy exerts a literal, physical force on material properties. The imaginary component only accounts for curvature. We turn now to the QGT's real symmetric part, the quantum metric. Mathematically, the quantum metric measures the infinitesimal distance between neighboring quantum states in parameter space. In a projection ontology, this is the local deformation and readability tensor. The parameter manifold acts as a flexible fabric that stretches and condenses to encode exactly how the projected electron relation alters as we move through momentum space. While Berry curvature tracks phase loops, the quantum metric tracks the wave function's internal texture and deformation. These properties are strictly bound by inequality structures. The metric stretching is mathematically constrained by areas of high phase twist, proving they are a single geometric reality. This resolves the anomaly of the flat band. Even when the material's energy gradient is exactly zero, the wave functions themselves are still dynamically changing their shape. The quantum metric supplies an interband geometric contribution that generates massive physical stiffness. Two bands can look identical on a scalar energy chart, yet carry entirely different internal deformation geometries. The collapse of energy-only realism is complete. For decades, this state geometry was inferred from secondary material responses. Today, experimental metrology allows us to chart these fields directly. This is a schematic of angle-resolved photoemission spectroscopy, or ARPAS. It fires incident photons into a crystalline solid, ejecting electrons, and records their resulting momentum and energy. Historically, the fluctuating signal intensities recorded during this process were treated as a mere nuisance, but recent breakthroughs revealed these are tomographic handles. Controlling polarization and spin resolution transforms these intensity variations into a pseudospin texture, encoding the block state's internal shape. The first major experimental proof of this method was the quasi-QGT reconstruction in the Kagame metal cobalt-10. Researchers successfully extracted precise geometric fields from a highly complex multi-band environment. This was followed by direct pseudospin tomography in black phosphorus. Because the material's structural symmetries suppressed the Berry curvature, researchers achieved a clean, isolated measurement of the complete quantum metric tensor. The instrument is not photographing a classical object. It measures a protocol-conditioned projection channel, turning abstract Hilbert space mathematics into a directly reproducible shadow-level chart. Energy is not the hidden physical substance that an electron is made of. It is a functional counter, a scalar value assigned to map admissible transitions within the shadow realization. This is the complete electron map. It begins with the scalar energy band as the base topographic profile, but it requires the addition of flowing holonomy actors from the Berry curvature, all bound by the continuously deforming grid of the quantum metric. This geometry does not represent an additional reservoir of free energy injected into the material. It is purely a geometric descriptor of how the projected state manifold is oriented. Even with this unprecedented clarity, the QGT remains the map, not the territory. It is a highly precise shadow chart, not a direct view of the underlying four-dimensional counterspace. We must rigorously delineate three distinct levels of geometry: the invariant 4D source relation, the measurable shadow-level QGT fields, and the measurement-level ARP's readout. Any cartographic mapping of a band structure that lacks this quantum geometric layer is an incomplete picture of electron behavior. Asking what shape the electron actually is constitutes a category error. It relies on the flawed assumption that particles are tiny, self-contained objects. But dismissing Hilbert space wave functions as purely abstract mathematics also fails, because that geometry yields measurable physical forces like flat band superfluidity. Under the TCGS-SEQUENTION framework, electron geometry is explicitly defined as the structured projection grammar by which a deeper source-level relation becomes readable to our instruments in 3 dimensions. The experimental accessibility of the QGT moves condensed matter physics definitively away from an outdated particle ontology and grounds it entirely in state geometry cartography. To map the true nature of matter, we must look past the scalar values of energy and learn to read the geometry of the projection itself.